Hello and welcome back to a new lecture series. In this one, we will understand a very interesting topic. We will understand the GTN model. So this GTN model is used in a specific area of crystal plasticity. It is called porous plasticity. So it deals with how materials fail by accumulation or coalescence of voids. Okay, that's why the name is porous plasticity. Porous means pores, P-O-R-E-S, which also means voids. So we'll understand this GTN plasticity model, and we will also look into how to club this GTN model with phase field. Of course, this channel will primarily deal with phase field modeling of fracture, as my previous lecture series was. So we'll understand how this GTN model is clubbed with phase field and how do we implement it in Abacus in an explicit format. Okay, we will not discuss implicit Abacus in this one. We will discuss explicit format. That means it is time dependent. Okay, so the phase field equations will be time dependent. So we'll start with this introductory lecture where we'll understand the GTN model. It's very, very subtle mathematics, and how do pores coalescence, or how do pores accumulate in order to give rise to fracture. So we'll study how metals fail from tiny voids to complete fracture. So this is part 1 of our lecture series, the mathematics from the ground up. So why do metals break? This is one of the key questions that we ask when we study fracture mechanics, right? And when we study fracture mechanics of particularly metals. As you know, metals or metallic alloys are primarily ductile, right? They are not brittle. So what causes what causes these ductile materials to fail? Because they don't have any cracks beforehand, right? They get cracked after, but they get cracked after quite a lot of plasticity, right? So a metal bar, it does not snap like glass. It stretches, thins and tears. So something is happening inside the material long before it visibly breaks. As I said, it will experience a large amount of ductility before actually cracking. Okay, as you are familiar with, phenomena like necking. All of you must have heard about necking, right? So necking is one such phenomena which makes metals flow, and after that necking we see a crack. Okay, so something similar is happening here. So the first point, we can have microscopic holes. Okay, tiny voids are born at inclusions and impurities. Correct? A metal can never be pure metal. So it will have inclusions, it will have impurities. And those inclusions and impurities will make the material very, very heterogeneous. And when a material is heterogeneous, it will have different solid mechanics parameters in different positions, such as, it may have different Young's modulus, it may have different fracture toughnesses, it may have even different Poisson's ratio. We don't care. What we care is the material is heterogeneous in different positions, and that heterogeneity will lead to microscopic holes when a material is stretched. Correct? I hope I'm clear. The second point, these microscopic holes, they will grow. Okay, by holes I always means pores or voids, because we are dealing with porous materials. Okay, or we are trying to make you understand why metals break due to pores. So these microscopic holes, they will grow, and when they are under stretching, these voids expand and multiply. Correct? It's self-explanatory. Now, After these microscopic holes, they grow, they become macroscopic, correct? And when they become macroscopic or largely microscopic, they tend to merge. And when they merge, we call the voids are coalescing. And after coalescence, they give rise to a permanent deformation or permanent crack. Okay? So voids link up into a crack and we finally say that the material has failed. So if you look here, nucleation. What is nucleation? Nucleation is formation of voids. Okay? So when you stretch a material, you see formation of new voids. This phenomena is called nucleation. Then these small voids, they will grow. Okay? And after they grow, they coalesce to give rise to a main crack or a primary crack, which is this red one. It is a very ideal situation, so don't scale this red curve. You just understand that these voids, after they grow, they coalescence and they give rise to a main crack. So we have nucleation, then we have growth, then we have coalescence. Okay? So we start, when does a metal yield? Okay? Until here, we were dealing with why do metals break? They break because of voids, okay, or because of void formation. Now, when does a metal yield? Okay? Crystal plasticity says a solid void-free metal starts to deform permanently. Okay? Permanently means it has large deformation. So it starts to deform permanently when the stress reaches the yield strength. It is basic theories of failure. So when your equivalent strength, it crosses the yield strength, that means it crosses critical stress, it will fail or it will start yielding, correct? So if you see your typical stress strain curve, your curve goes like this, it reaches yield point, and beyond that we see that the material has yielded. It may or may not break, but it has yielded. Okay? Yielded means it starts to deform permanently. Correct? Understand this very, very carefully. Yielding is not breaking. Yielding means it starts to deform permanently. Okay? If it is a brittle material, this permanent deformation or this yielding phenomena will lead to breakage. But if it is a ductile material, this yielding will lead to plasticity. It will not lead to breakage. Okay? So this is the basic difference between a brittle material and a ductile material. You have to get your solid mechanics straight. Okay? So if we have to define mathematically this yield function, this yield function by a character capital phi, we say that this phi is sigma equivalent minus sigma y, and in critical conditions this will be equals to 0. Correct? Sigma equivalent is your equivalent stress of the body that it is experiencing at every time step. And when this is equals to the yield strength of the material, we say that the body has started yielding. So this is the critical condition for yielding. Okay? The equivalent von Mises stress, so this equivalent stress sigma eq is the equivalent von Mises stress, and this measures how hard the material is being distorted. Mind this word, distorted. When does a material distort, or due to which stress component does a material distort? It distorts due to the deviatoric part of the stress. Correct? So sigma equivalent is defined by this formula in plasticity, where this Sij is the deviatoric part of the stress tensor. Okay, I hope this is clear. The key limitation of this this basic model is that this model never lets the metal break. It just keeps flowing forever. Because as I said, there is no failure criteria here, right? This yield function, when phi is greater than 0, say, that means what? Sigma equivalent is greater than sigma y. That means it has started to deform permanently, but it will not break. Okay, so this model, it does not have a failure criteria. That's why its key limitation is that this model never lets the metal break. It just keeps flowing forever. So it is huge ductility, but never failure. Okay, I'm repeating my words quite a lot, but it is just to emphasize how important this basic formulation is. So we have to introduce a failure criteria, right? And I explained that if you introduce voids in the ductile zone, those voids can coalesce and give rise to a main crack. So the one new idea, porosity. Okay, so this person Gurson, he adds a single number to track the damage, which is called the void volume fraction small f. Okay, in this whole presentation, I actually made it very fast. So this syntax of F and there will be an italic F, those are same. So what did Gurson do? He defined this F. Okay, this F is the void volume fraction divided by the total volume of the body. Okay, I'm sorry, it's not the void volume fraction. F is the void volume fraction. V voids are the volume of the voids, and V total is the total volume of the body. So F is the void volume fraction. Now, when F equals to 0, you have a fully solid undamaged material because there are no voids. When F is small, you have a very few tiny microscopic voids. So this is the early signs of damage. And when F is large, the voids dominate and we say that the material is near failure. Okay. So what was Gurson's insight? You see, it is 1977, so it is a pretty recent work. So Gurson rewrote the yield condition so that porosity weakens the material, as we have discussed. So when F equals to 0, it collapses back to von Mises. Okay, so he wrote a new yield function capital Phi, and that yield function, when it is equals to 0, he defined it as a function of this porosity F. Okay, so Gurson derived his yield surface analytically. It is very, very important. He did not do any kind of finite element simulations. From an idealized model, this model is what? A single spherical void sitting at the center of a spherical shell of a rigid, perfectly plastic material. So this is the problem that he took. He only had one void, one single spherical void sitting in the center of a spherical shell. Okay, and he studied the evolution of that single void. So this is the yield function that was defined by Gurson. Okay, you see, the previous yield function was what? It was only sigma equivalent minus sigma y equals to 0. But now you have this entire big function, which is again a function of what? You have sigma eq, you have sigma y, you have p. P is what? P is the pressure. P is the pressure or the load, the applied stress. Okay, you have sigma y, which is the yield stress. Again, you have F. So this F, this porosity has been introduced, and there is this cos h term. So as you know, cos h is a very unstable mathematical function. So just for a small argument, it may blow up. So this function, when you are trying to simulate in a finite element platform by writing your own codes, you have to be very careful of this cos h term. I will come into these in the third video probably. So yeah, for now you have this yield function. Okay. Now we see that pressure now matters. Why? The cos h term means squeezing or pulling on the voids changes yielding. Okay, so there is this new model versus the von Mises model. Okay, so what? Squeezing or pulling on the voids. So if you change this P is essentially what? Squeezing or pulling on the voids, and this will change yielding. Okay, so this yield function is heavily dependent on this P. As you will see, this P is a very important parameter that we derive, that we actually not derive, we calculate it in every time step when we go to abacus. Okay. Next, porosity softens. As F grows, the material yields at lower stress. Why? You see, you increase F, what will happen? If you increase F, this function will increase, correct? And if you increase F, this function will also change, correct? So the effective stress will lower. Okay, and when it lowers, we say that the material yields at lower stress. Now, how do we go from Gurson to this GTN model? Okay, so there were these two gentlemen, Tvergaard and Needleman. They added 3 calibration constants, Q1, Q2 and Q3, so that the model matches real experiments. These were introduced by Tvergaard after doing detailed numerical finite element studies of arrays of interacting voids. So if you remember the previous Gurson model, it had what? It had only a single spherical void, right? Now they have arrays of interacting voids. The Gurson model, it did not predict how voids interact with themselves. Okay, as I showed in my introductory slide, you saw that there are many voids that coalesce to form a new crack, correct? But the Gurson model was not capable of predicting that. Now you have this GTN model that considers arrays of interacting voids, and they introduce these 3 calibration constants. These are basically experimental constants. Okay, so they modified the yield function as this. So what is different? What is different from the previous yield function? Let me remind you. This was the previous yield function, correct? You see it very carefully. Now I go to this slide. This is the new yield function. So we have Q1 here, we have Q2 here, and we have Q3 here. Okay. So essentially, if Q1, Q2, and Q3 are 1, you get back the original Gurson yield stress, the yield function. I'm sorry. Okay. Now you have this F star parameter also. So when F star is equals to F, you get back the original Gurson model. And when Q1, Q2, Q3 are all 1, you get back the original Gurson model. Okay. Now, Q1 was taken to be 1.5. It is not universal, but it matches the the characteristics of most of the metals out there. Again, you are free to calibrate your own parameters with experiments, but this is what you will end up with, like more or less. So they saw that this Q1 needed to be ramped up a bit in order to match experiments. Okay, that's why Q1 was raised from 1 to 1.5. They didn't feel the need to increase Q2, and Q3 was found out to be Q1 square. Okay, so typically for most metals, you will find that these parameters are your do all and end all. Now, these Q values correct for how voids actually interact. The original Gurson theory was slightly too optimistic. Okay, why? Gurson's theory predicts the material is stronger and survives longer. Okay, why does it survive longer? Because if you lower Q1 to 1, you say that this sigma equivalent is actually greater than the sigma equivalent that you will get from here. Okay, so the original Gurson theory was slightly too optimistic. Gurson's theory predicts the material is stronger and survives longer than experiments show. It's optimistic about the metal's remaining strength. As I said, for the Gurson model, you will find a higher equivalent strength than the GTN model. Okay. So GTN is Gurson Tvergaard Needleman. Tvergaard. Okay. Now, we try to capture the final collapse. The final collapse means the final coalescence of these voids. So real metals fail suddenly once voids start merging. So once you have your microscopic voids, then they grow to become macroscopic voids. And when those macroscopic voids start merging, you literally will see destruction of the material. Okay, this process of macroscopic voids to merging to breaking is very, very fast. Okay, it's very, very fast and sudden. So real metals fail suddenly once voids start merging. GTN replaces F, the porosity, with an effective porosity F star that accelerates past a critical value Fc. Fc is what? Fc is your critical porosity. Just as you have your critical stress, you have your critical energy release rate, you have your critical SIF. Similar to that, you have a critical porosity. Okay? Because every metal that has voids, it does not fail, right? Only when the voids grow and cross a certain threshold, then only the metals will break. Otherwise, every material that you see out in nature, they have voids. You take any metal, you cut a cross section and put it in the scanning electron microscope, you will find voids. But then why are those materials not failing, or why are those metals not failing? Because the voids have not reached criticality, or they have not reached coalescence. Okay, that's why defining a Fc is very, very important. Okay, so this F star is defined like this. So when F is less than Fc, you have F star equals to F, which is the original porosity. This F star is called the dynamic or effective porosity. Okay, so this F star is equals to F when F is less than equals to that threshold value of Fc, and when it is greater, the F star, it scales like this. Okay, so Fu star is 1 by Q1 minus Fc by Ff. Ff is the porosity at failure. This is the porosity at criticality, not failure. This is the porosity at failure, which is usually it is higher. It is much, much higher than this value of Fc. Okay. So Fc plus Fu star minus Fc by Ff minus Fc into F minus Fc is what this dynamic porosity will become. This dynamic porosity, let me remind you, where does it come? It comes here and here. You just replace F in the Gurson model with F star in the GTN model. So if you take a look at this curve of effective F star versus the void volume fraction F, you see that until here you have F star equals to F, or you have no acceleration, no porosity acceleration. And this curve, it represents F star, or this equation where it is accelerated. Okay. As I said, where is this acceleration coming from? The fact that the real materials fail suddenly when they reach coalescence. So once it reaches coalescence, once the void starts accumulating, the material fails suddenly and it reaches FF. Okay. So that is what is called coalescence acceleration. That is how accelerated the crack forms after void coalescence. Okay. So beyond Fc, the effective porosity shoots up, thus modeling coalescence. Now, how does porosity evolves? How does porosity evolve? The void volume fraction changes for two reasons. Existing voids grow and brand new voids nucleate. Okay. So you have some existing voids, correct? Now, how do these voids give rise to a crack? There can be two phenomena, right? The existing voids that are there, the existing microscopic voids, they have to grow in size. So the existing voids grow, and if they don't grow in size, they will have to nucleate. Correct? So there should be brand new voids that are nucleating, or there must be some brand new voids that are forming. Okay? So the existing voids, it can grow. This is one phenomena. And the second phenomena is some newer voids can come up. Okay? This phenomena is called nucleation. So you model the growth of porosity F dot. I mean, loosely I mentioned growth, but not. You can say that this is the evolution of porosity F dot, and it has the growth of voids, which is this term F dot growth, plus brand new voids nucleate. So the nucleation of voids, which is F dot nucleation. Okay. So what is growth? Existing voids expand as the material stretches plastically. Volume conservation of the solid. Okay. So to conserve volume, the existing voids expand as the material stretches plastically. So this is how you define this F dot growth, which is 1 minus F into epsilon P kk dot. This is the trace. So what is epsilon kkp? Epsilon kkp is the trace of the plastic tensor, plastic strain tensor, and you have to take a time derivative of it. So you are basically looking at what? You are basically looking at how the trace of the plastic strain tensor evolves with time. Am I clear? I should be clear. So this epsilon kkp dot is the trace of the plastic strain tensor, how it evolves with time. And once it grows with time, you also have to account for F. So if F increases, what will happen? If F increases, that means your porosity is growing. So more and more voids are what? The void volume fraction is increasing, right? So more and more voids are growing in size. So if F increases, this 1 minus F will decrease. Correct? And if you multiply this 1 minus F with the growth in the trace of the plastic strain tensor, you will find out what is the rate of growth of the voids. Now we come to nucleation. Nucleation is what? New voids appear as plastic strain accumulates following a statistical Gaussian law. Okay, there should be a basis of how new voids are appearing, right? So usually this F dot nucleation term, it is usually taken as this, capital A multiplied by what? Multiplied by the equivalent plastic strain, again derivative of that, derivative with respect to time. So this is what? This is the rate of change of equivalent plastic strain. Okay, this is the rate of change of equivalent plastic strain, and multiplied by this capital A. This capital A is actually this statistical Gaussian law. So what is nucleation intensity? It is Gaussian in plastic strain. So nucleation intensity is this capital A, which is this distribution. This is what? This is the normal distribution, right? This is a normal distribution. Fn is the nucleation porosity. Okay. Sn is the standard deviation, and epsilon n is the mean of the plastic strains across a wide range of increments. Okay. So you have a distribution which is Gaussian in plastic strain with a mean of epsilon n and a standard deviation of Sn. And you take this Gaussian expression of capital A, which is the nucleation intensity. So you always, if you have to define terms like this, some growth of porosity, you always have to multiply some porosity term with the plastic, with some component of the plastic strain tensor. That depends on how you want to model it. Okay, suppose you come up with a model that that has growth nucleation plus something else like shear. Okay, so there will be what? There will be another F dot shear term, and that F dot shear term will also contain a term of porosity and a term of the plastic strain. Any term, any component of the plastic strain multiplied together. Okay, so this is a general form of how you define the growth of your porosities, various porosities due to various processes. So coming back, hardening. This is another very important phenomena. Okay, so as and when your sigma increases, okay, so your sigma increases, it crosses the elastic limit, it starts yielding, but also the metal starts to harden, and that hardening will obey a particular law. There are many hardening laws out there, but I am taking the most simple out of them. Okay, so hardening, the yield strength itself grows with strain rate and temperature. We take the Johnson-Cook hardening model. So the Johnson-Cook hardening model is this. So this yield strength will itself grow with strain rate and temperature. This is hardening. And when does it happen? It happens beyond the elastic limit. Okay. So sigma y is defined by this long expression. So it grows with strain, which is this term, A plus B epsilon EQP to the power n. So this epsilon EQP is what? This is the equivalent plastic strain, and A and B are some stress constants. Okay. A is the initial yield strength of the material. B is some strength constant, which is multiplied by this equivalent plastic strain raised to the power of n. N is the hardening exponent. Okay. Now you have strain rate, which is this term, 1 plus some constant multiplied by log of epsilon dot star. Okay. And you have this temperature term, which is 1 minus T star to the power small m. This T star is called the homologous temperature, and this is beyond the scope of this basic GTN law. But again, if I make a video about Johnson-Cook separately, I will be explaining in detail about this entire equation and how it comes. Okay, so stay tuned for that. Right now, just remember that this T star is called the homologous temperature, and this T star arises due to ambient temperature and the instantaneous temperature of the body. Okay, and that has a temperature exponent. So you have strain hardening, which is this term. You have rate sensitivity, which is this Y rate, because epsilon dot is called the strain rate. Okay, and you have thermal softening, which is this term. Now, to conclude, we put it all together. The metal fails when porosity reaches its final value. So F, when it reaches some FF, the element loses all its strength. Why? Because as I said, FF is the largest porosity that the material can achieve. Okay, FF is not FC. FC is the critical porosity, and FF is the failure porosity. So beyond FF, porosity cannot grow. If porosity reaches FF, we say that the element has lost all its strength. Okay. So we track one number. We track the porosity F, which captures the damaged state. Then we saw that porosity weakens yield. So the GTN surface, it couples pressure and porosity. Voids grow and nucleate. So evolution laws drive F upward. Correct? The evolution laws are what? The growth and nucleation. And when F tends to FF, it means failure. Effective F star accelerates the collapse. Why? Because it contains FC, it contains FF, and it also contains the term 1 by Q1. That's why it accelerates collapse. So, in the next video, we will see what happens when we couple GTN to a phase field crack. Because that is what our aim is, right? We have to couple porosity with phase field. And we have to understand how it works in abacus. So, we will look at what happens when we couple GTN to a phase field crack and how it all runs in abacus. So, stay tuned for the next video. Thank you and see you.